So this paper club is a little bit different than other ones because I chose that tutorial to present instead of actual paper. I found that tutorial because so we have at nPlan, we have an academic advisor from Oxford. His name is Yaron Gall. And every so often he suggests some stuff to us. And last time, maybe like a month ago, I asked him if there was anything that he thought that we should keep abreast of in machine learning. And he said, I think you should check out normalizing flows and flow matching. It seems like that's an up and coming form of generative modeling. And there's a good tutorial on it here. And so he sent me this tutorial. So I'm going to try to walk you through my version of like this tutorial. I've left stuff out. Like I actually feel that we can get a better understanding of the tutorial without going into all of the math that they did in the paper. I mean, in the tutorial. But I'm happy to go through any questions you might have. And yeah, I really like doing these types of presentations because they're pretty mathy, but we get to go into we get to go through some cool basics, interesting math as part of it. So I hope you enjoy it too. There's one more section that I'm going to be doing. But so the sections that I'm going to be doing in this presentation are, I'm going to talk a little bit about generative modeling generally, then talk about normalizing flows, which is a type of modeling paradigm for generative models, continuous normalizing flows, a type of normalizing flow model, and then flow matching and flow matching with optimal transport. Hoping that each section follows on from the last, and hoping that it all makes sense, because yeah, this tutorial went through so much, even though it was quite long, but like it went through a lot. But like, okay, let's start off with like a basic definition of generative modeling. So I think, you know, when ChatGPT hit, the term generative AI became really huge. But actually, ChatGPT and language models aren't the only form of generative models or generative AI. There's actually a ton. And it's a much more abstract thing than just like autoregressive large language models. So the real definition of, in my opinion, of generative modeling is you have some data set of examples. Usually you assume that they're independently and identically distributed. And you want to estimate the data generating distribution. Over here, I'm calling it Q of X. So you want to know what the likelihood of each example is, and ideally you want to be able to sample from it. But so you're trying to figure out, like trying to estimate that distribution given a data set of examples from it. And there's a couple of different use cases for generative modeling that I wanted to highlight. The one that has really changed the world in the last couple of years is actually sampling, and specifically conditional sampling. So when we call ChatGPT or other large language models, what we're doing is we're providing the beginnings of a piece of text, and we're asking it to complete it for us. And that's called conditional sampling, because the beginning of the piece of text is the conditioned text, and then you're sampling to get the rest of it. So one really important use case for generative modeling is sampling and conditional sampling. And I think we're going to continue to see in so many different areas that being something that is really useful. The second use case for generative modeling is likelihood estimation. So figuring out how likely an answer is, or how likely a sample is. You can use that to do things like figure out how confident your model is in an answer. But there's a lot of other use cases as well. And also that's something I think we would like to be able to do. It's not something that I see being done as frequently, but it's because it's actually quite hard. Like you can't use the likelihoods that come out of a large language model to figure out the likelihood of an answer, because the answer space is infinite. And then the last one, which isn't talked about too much, but we do use it under the hood in a lot of different places, is representation learning. So we actually sometimes use generative modeling for representation learning. So you want to come up with like usually a compact description of some much larger piece of data that then you can use downstream for some use case. Like, for example, you want to describe a book in a vector embedding so that you can use that information as part of your answer to as part of your answer to a question, or maybe you want to take a video and you want to describe it as like a sequence of vectors so that you can generate the next frame. There's a ton of different use cases. One that I wanted to highlight, because if maybe a lot of you have seen before Disney plots in papers and stuff, but so Disney plots, or Disney as a method, is actually a form of generative modeling that is used for representation learning, where you're actually trying to approximate the distance distribution between points in your original data set in a lower dimensional space. And then so one example of conditional sampling from image space is what we see here, actually in reverse. So you might start with like Gaussian noise, and then you condition on that want to sample an image from your distribution of like your data set of flowers, like a new image. So this picture is an example of conditional sampling. One approach to generative modeling that to do, usually it's to do 1 and 2, is you take a simple distribution that's easy to sample from, and then you transform it into a complex distribution, which is the one that you're more interested in. So I chose this picture, which is from, I think it's from like a diffusion paper. And what you can see is like, if you look all the way on the right, on the left, we have like our distribution of interest, which is like it looks like a Gaussian or something like that with 2 modes. And then through some transformation process, we transform it into a single Gaussian distribution, a simple Gaussian distribution. And then you could go in the opposite direction. So this is a really common approach, because like then sampling tends to be much easier, because you can just sample from the simple distribution and transform it. And also, depending on how you do it, the likelihood estimation can be fairly straightforward as well, but tends to be harder than other models. But one thing, so this basic approach of transforming a simple distribution into a complex distribution in a reversible way, which is what you're seeing here, this has been like it's like half of the generative modeling that we see these days, because that's what diffusion is. Like diffusion models, which are being used for image generation and for video generation, a lot of different modalities besides text. And even in text, they're using this approach. They're starting to use this approach to generate pieces of text as well now. So we're seeing it in a lot of places. I think, I forget what's the name of the model that does text generation this way. We had it going through our Slack at nPlan recently. If anyone remembers, let me know, like what's the diffusion-based model. Anyway, but yeah, the one approach is transform a complex distribution into a simple distribution in a reversible way. So what's one way to do this? One way to do this is what's called like a normalizing flows approach. And so say you have some distribution Q0, which is the distribution that you're interested in learning. Excuse me. And so you can sample from Q0 to get samples X. And then you have some transformation that goes from like the space, basically like if X is a vector with a certain number of thanks, David. If X is a piece of data that has a certain number of dimensions, like let's say for an image that's 64 by 64, it's 64 squared dimensions, then you have a transformation that keeps the dimensionality of your input and like the same domain basically. So if you have a transformation that goes from the input space, like from the to the same, like sorry, from the same space to itself, and that transformation is continuously differentiable, and it has an inverse which is continuously differentiable. So key point is it has to have an inverse and it has to be continuously differentiable, because not all functions have an inverse. Then you might ask, like, what is the, so one way to do this transformation is with this function phi, and you might ask, like, what is the distribution of y? So you take all of the points in your domain X, or like your support for your distribution Q, and you transform them into y. Like, what's the probability distribution for that? So there's this pretty complex looking equation which tells you what the distribution is. So we know maybe we know Q naught, but we want to know what P would be. And you can use this distribution, which is just saying, like, I like the bottom one a little bit better. It's saying, okay, P of y is equal to the likelihood of X for Q, which we know, and then divided by the absolute of the determinant of the Jacobian of like the transformation. So I just wanted to quickly introduce the Jacobian, or talk about the Jacobian. So say your output has 3 dimensions, X, Y, and Z, and your input has 3 dimensions, U, V, and W. Then the Jacobian is a matrix which is like basically the derivative of every output divided by every input. So I hope this equation here makes that clear. And basically what it does is it describes how small changes in an input like dimension can affect an output dimension at a given point. And so my intuitive explanation of these equations here is that, like, the Jacobian describes how much spreads. Sorry, one second. How much phi spreads the density in a space around y. So yeah, it's telling you how much, maybe it's like compressing, so there's more density around the points in for p, or maybe there's less density, and so that's what this value is doing. Yeah, that's pretty. I'm hoping that's as mathy as we'll get. But so now we have. If you remember, we want to transform a one distribution into another, and we want to train a model to do that. So we have this normalizing flows way of doing that with these equations. And so what we can do then is we can parameterize phi with a neural network, and then maximize the expected value, like the expected log likelihood of each point in our data distribution. So like you transform each point in your distribution to this new simpler distribution, and then you maximize the likelihood. Hope that makes sense. So that's one way, like transform and maximize likelihood, as opposed to often with generative modeling where you're just doing like maximize likelihood. But there's some issues with this approach of normalizing flows as it's been described, or there's some challenges. So first of all, phi, the neural network, has to be invertible. It has to be possible to compute phi's inverse. It also has to be computationally efficient to compute phi's Jacobian at each point, which is hard because, like, in most cases, computing the Jacobian would mean that you have to like do a backward pass of your network, like as many times as there are inputs into the network, or into phi. And then one issue is, like, for many of the models phi which meet all these constraints, they're not very expressive. So like you can use a linear model like y equals mx plus b that satisfies all of these constraints, but it's not very expressive. So like say that the distribution that you want to learn over images, like you want to learn all the images of cars, that could be very complicated. And so if you're using very simple flow networks, normalized flow networks phi, you won't really be able to approximate it easily. So you want something which is both meets all of these constraints and then also is quite expressive. So it can transform like a relatively simple distribution into a very complex one. So that's where, excuse me, that's where residual normalizing flows comes in. And this is this is a way of describing your flow network phi, and it's really simple. It's like your input plus some constant times a transformation u of x. And the constraint for these residual normalizing flows is that they have to be like 1 over h Lipschitz, which is Lipschitz is like it's a constraint on how, or it describes how quickly something changes between 2 points. That's like a simple way of describing it. So you need, and there needs to be like an upper bound on how quickly those two things, how fast a function changes between 2 points. Won't go into it too much, but so 1 over h Lipschitz means that the Lipschitz constant, so the maximum rate of change that you see has to be 1 over h. And so for residual normalizing flow networks, that's the constraint that has to be met in order for for phi to be invertible, and also for it to be invertible. And then the way that you can approximate the inverse, so getting the phi to the -1, is that you can use something called a fixed point iteration, which is pretty simple actually. It's like you start checking points, doing a forward pass until you find the one that gives you the correct value that you were looking for. But anyway, so you can, if this is 1 over h Lipschitz, you can use fixed point iteration to calculate the inverse. So for residual normalizing flows, if we go back here, you know that 1 and 2 are checked, and maybe the Jacobian isn't very hard to calculate. They don't really mention it in the tutorial. But the big benefit of this approach is that the normalizing flow network phi can be highly expressive, since its Jacobian can be full rank, which means that like basically you can the number of, I won't go into full rank, but it basically means that you can have a highly expressive normalizing flow network, which is and still meet all of the constraints that we were talking about before. And that means that you can approximate a lot of different data generating distributions with this approach of transforming a simple distribution into a complex one. Yeah, I said that. There's also, so for this this approach to normalizing flows, there's also a nice property, which is that flow functions are composable. So you could take, like, if all your flow functions look like this, then you can just take all of them and add them together to create a new one, and you know that it also will be a normalizing flow function. So you could have like 5 of them that are all residual normalizing flow functions, just add them together, and you know that it's going to be a normalizing flow. Or not add them, but like compose them. So you call one after another, and you know that it's going to be, it's still going to be a normalizing flow model. And what that means is it's actually pretty easy to compute the log likelihood of residual normalizing flows, which is also something that we have to make sure is correct, that we can do, because if you remember, if we go all the way back, the objective that we're using to train these networks is we're trying to maximize the log likelihood of the distribution that we're transforming into. Okay. Okay, but you know, residual flow networks aren't perfect. Residual normalizing flow networks aren't perfect. One thing is that, as you can imagine, like as you add more normalizing flow networks onto the model, so more of these phi subscript some integer networks, the more expressive it gets. But then the question is like, how many do you add? Because the more you add, the bigger the model is, the more data hungry it is, the faster, the longer it takes to compute, all of these things. And the other issue is that, like, in order to ensure that the process is invertible, not only do you have to make sure that the flow network is invertible, not only do you have to make sure that it's Lipschitz, but you actually have to make sure that it's 1 over delta Lipschitz. So yeah, it's a harder constraint to meet, and it constrains the model more that you learn. So there's these two issues with residual normalizing flows, and that's why we get continuous normalizing flows as like the next iteration, or like improving upon these issues. And so if you take a normalizing flow network that's a residual normalizing flow that has this equation here, and you rearrange it, you get something that looks like this. And as they point out in the tutorial, this looks a lot like a derivative, because it's like the difference between 2 points divided by a small constant. And if you take this difference in the limit, then what you get is, as delta gets smaller, what you get is that the change in x over time is equal to that residual network. And then what you can do is you can say that like xt is equal to x naught plus this integral over here. I'm just going to go back really quick so you can understand what that means. Or I hope this helps. It's like, so say you have some point x naught that's in the distribution of data that you have, then the path from here to here of this x is defined by that equation that we just showed. Sorry, yeah, right over here. Is defined. So you would say like, okay, I want to know what x is at time 0.5. Then it's x naught plus this integral from 0 to 0.5. And excuse me, but you know, this tells us how to get x of t. But if you remember, we're not trying to, we don't train the model by calculating x, the endpoint. So we don't train the model by calculating what, if we have x naught, what like x1 is. We train the model by maximizing the likelihood of x1, which, sorry, the likelihood of x1. So we need to be able to compute the likelihood of x1 for this new approach where we're defining like a continuous normalizing flow with this residual network U. Luckily, with some like fancy math, there's an equation for that, which is like, so you know your p naught, your initial distribution, and you know x naught, like the initial data point, and then the likelihood at each time, especially like the endpoint, which is what we want to know, p1, is equal to this equation here, which is the initial log likelihood, the initial log likelihood minus the integral of the divergence of u of s from 0 to time t, or time 1. So the divergence of a function is not something that, I think if you do partial differential equations, you cover it. I might have covered it when I did partial differential equations when I was studying mechanical engineering undergrad, but I don't really remember. So I thought I would do a quick review of divergence. So what is divergence? I like this explanation on Wikipedia. It's like, in physical terms, the divergence of a vector field is the extent to which the vector field's flux behaves like a sink or a source at a given point. It is a local measure of its outgoing ends, the extent to which there are more of the field vectors exiting from an infinitesimal region of space than entering. Yeah, that's still pretty technical, right? So I thought this diagram might help. So you have some point in space, and you have like a vector field, which is just something that's like defining vectors coming from, like defining a vector at each point. And so the divergence is saying like how many of these vectors are pointing into the point, and how many of these vectors are pointing out of the point. So you can see here like they're all pointing out, which means that the divergence is greater than 0, which means things are like moving out of the point. And in the next case, all the vectors are pointing into the point, which means the divergence is less than 0, which means things are going in. And then over here, you can see all of the field vectors at that point are pointing up or down, so they like balance each other out. So there's no like things being collected or being removed from that point. It's tough because, yeah, Arvin?
Yeah, we just recently read another way of looking at it is if you take any point and put like a small ball around it, the average of the function on that very, very small ball, larger, smaller, or the same as the value of the function at that point you draw the ball around.
So it's like
of course the same thing, just a different way to look at it.
Yeah. So that's saying that like if you took the difference between the function value at that point and like around it on the ball, you would get the divergence.
Yes. Sorry. No, I got it wrong. That is Laplacian. But
Okay.
Laplacian is the divergence of a vector field. Yeah. Sorry. Yeah. No, never mind. That was stupid.
No, I think it's a similar idea. The whole point is like you could think of it like as, are things going into this point or are things going out of that point? And so this is how you would calculate the divergence. You have the function with respect to each of your you have the derivative with respect to each of your input dimensions, and then the output of the function with respect to each of those dimensions, because in these functions, you know, if there's a 10-dimensional vector going in, there's a 10-dimensional vector going out. And then you just add up the these derivatives. And I think I know I didn't give a great explanation of divergence, but I think that really helped me kind of understand what's going on, because like, so what this is saying is like they're calculating the divergence of this function at each point in order to calculate the likelihood. So your likelihood is a single number. And so this divergence, it's like basically saying how much probability density is leaving or entering the distribution at this point for each point along the integral. So it's counting up how much the probability density is leaving or entering the point so that you can calculate the new probability density. Yeah, I hope that's at least a little bit helpful.
Would that be then exactly this inverse of the determinant of the Jacobian? Because that sort of is the stretchiness factor, or whether it's a single source or 1 minus that?
Yeah, that's a good point. I was actually wondering how, because in the tutorial they say like, but how do we compute the Jacobian? And then they go into all this like continuous math that has nothing to do with the Jacobian. And so I think that that's a good point, that this is like the equivalent of calculating the determinant of the Jacobian in this continuous case. Yeah, actually that makes a lot of sense, because this would be like the trace of the Jacobian, right? Anyway, which is similar to the determinant. Okay. So we talked about that. So now we know how to calculate the log probability of the transformed point x and the transformed point x. So with continuous normalizing flows, what we usually do is we define an ODE that has both of these variables as part of the ODE, as you see here, and then use an ODE solver to forward propagate the original point. And then once you've done that, you maximize the likelihood of the final distribution that is your like what I call like the simple distribution, and you're trying to maximize the points for. But there's some problems with this approach. Like, it's not perfect. One of the big problems is that training is very expensive because you need to use a numerical ODE simulation to compute the likelihood. So like every time you, we go all the way back, sorry. Every time you want to train, to calculate the forward pass of your model, of your approach, you have to actually like propagate a point from here to here using an ODE simulation. Which could require like, I don't know, hundreds of calls to the model that you're training. So it's expensive. The second thing is that in higher dimensions, you actually have to estimate the divergence, I think, in order to make sure that it doesn't take too long to calculate it. So you need to have a good way of estimating the divergence at higher, like for higher dimensional inputs. So like with images. And one thing I wasn't sure about when I was reading is like, does this mean that when you do the full back propagation from this approach, where you perform the OD simulation and you get your output and you're like, okay, now I need to back propagate through it. If you have to calculate the Hessian because you're calculating the divergence, which is like the gradient of your network with respect to the inputs. I wasn't sure about that, but anyway, that was a question of mine. And then another issue with this continuous normalizing flows approach is that sampling also requires like an ODE simulation, because you need to go from like your simple distribution to your complex distribution. That's not addressed with what comes next. They don't really talk about that part of it. But I think now they're just focusing on like, how can we make this training approach tractable and or like more efficient? And that makes me think that maybe this approach is really effective, and so they don't care the fact that you still have to do these ODE simulations in at inference time to sample. They're really effective at generating high quality samples. So just to recap here, so with this continuous normalizing flows, the big problem is that you have to do these ODE simulations to compute the likelihoods. And that's really expensive and means training takes forever. And we don't want training to take forever because we have a limited amount of time in life. So this is where they introduce the new approach, which is one of the main parts of this paper, which is called flow matching. And this removes the need to perform an ODE simulation at training time. And by what you're doing is you're specifying a probability path that the function should take. So instead of having to calculate this log probability at each point, I mean, for each point, like and fully transform your initial point to your endpoint and calculate the likelihood, all you do is you actually like sample some time t from 0 to 1, and then you calculate with some reference flow network what the value should be, and then you take the difference between the two and you minimize the mean squared error between the two. So it's a lot simpler, but there's a rub here. Like, like just obviously the whole point of this process is to learn you. So if you already know what it should be, then what's the point of learning it? So actually, you can't just do flow matching by itself. That wouldn't work, because if you already knew you wouldn't have to learn it. So you can't train u of theta with u. But what you can do is you can condition on a sample from your data set when you're doing this whole process. So this is called conditional flow matching. And then what you're doing is you're saying like, okay, well, here, what you're saying is like, I don't actually know where this point is going to go. Like when I do this OD simulation, I don't know where the point is going to end up. But over here, you say, I do know where it is because I know what point I wanted to end up at, or I know where I wanted to start. Because you're conditioning on it. And I'll go into a lot more detail on this, but I just wanted to, the reason why all of this works, why this is so good, is because the gradient of this objective over here, which is the flow matching objective, and the conditional flow matching objective are the same. So you know that if you use the conditional flow matching objective to train your flow model, then you'll get the same model as if it was your flow matching, as if you were training it with the flow matching objective. That's the whole reason why it's so good. So how do you choose if we go back, how do you choose what your reference this function is going to be? How do you choose what that's going to be? So first you define some boundary conditions. Your main boundary condition is that like the original distribution over points is the same. So you have your simple network, which is your simple distribution. Just so sorry to go back all this way, but here for me the simple distribution here is this like Gaussian, and the complex one is this this two-mode distribution. So you say like, I want my initial points to be Gaussian distributed, and then we'll go all the way here. Yeah, and then you say, okay, at time 1, at the end of my simulation, I want my my points to be distributed such that it reaches a specific point in my target distribution. So you say like, okay, I want my initial points to be Gaussian distributed, and that's my boundary condition 1. At time 0, the points are Gaussian distributed, and at time 0, at time 1, I want it to reach this like picture of a cat or something. I want it to this specific picture. And usually you also have to define the path between those 2 points. So you say, and I think what they do is they use a straight line. So now let me try to explain how this all works. Excuse me. What you do is you say, okay, so you want to go from this distribution here to this distribution. Yeah, go ahead, Arvid.
So yeah, that was something I was slightly struggling with the paper. So you do purposefully line up points at this point, right?
Yeah.
Yeah. Okay. Thank you. Yeah, that was what confused me, because of course you don't know the initial distribution itself. This corresponds to the points you're gonna get out on after the transformation. So you sort of have to make that mapping. Sorry. Yeah.
Yeah. So what they actually do, and you can see it from here, is so say this is on the right is your simple distribution. They'll sample points from the simple distribution. They'll sample points from your picture. This is your pictures of cats on the left. They'll randomly select a batch of cat pictures, and then for each one they'll randomly sample from the simple distribution, and they just say like, this sample from the simple distribution has to go to this picture of a cat, draw a straight line between it, and then they like choose a point on that line in order to as their training objective.
And during training they would keep that sort of fixed, right? So say if you train over several epochs or so, you wouldn't break that connection between input point and output point, right?
Actually, I think they do break it. So each time they randomly sample a new point from the simple distribution.
Okay.
But what's interesting about that, and that's what leads to these like crossing paths that you see. What's interesting about that is when you use the network you've trained, this is what like all the paths look like. And that's because they're using an ODE solver to go from like from right to left, and ODE solvers have this like, so I'll just go quick. So
those were different methods, right? I think in these pictures, the left hand was the conditional method, and the right one was the
marginal.
Yeah, we train it differently, essentially, where
Well,
these
so
always are laminar or at least non-overlapping. Yeah.
so actually, what it is that like these are using the same models, but like this is the conditional one and this is the marginal. So this is when you like integrate over. They know what the marginal u of t of x is for each point, because they chose a specific example where they know it.
Yep.
But so they're what that means is if you train using this approach, you'll still get paths that look like this that are not intersecting.
Yep.
And that's because of the uniqueness of ODE solutions. So like, if you remember over here, at sampling time, you're using an ODE solver to go from right to left. And like a fundamental theorem in ODE theory states that for well-behaved ODEs, which a lot of them are, given an initial condition, a starting point, there's a unique solution curve that passes through that point. So like for each input point on the left, on the right, there's a unique line that the solver will give you that goes to the right. And what that means is that like when the solver is actually creating these paths, there can't be intersections between, like if you choose a unique point on the in the input space and you use the ODE solver to go to the output space, you can't have another, the path can't cross with any other path with any other point in the input space. Because if it did, then you wouldn't have like a unique path. You'd have a couple paths that would lead to the same point. Yeah.
Is it still intuitive that neighboring points have similar flows in the marginal form?
Well, so they don't always have similar flows. Here they do, but I was about to show an example where that wasn't the case.
Yep.
So yeah, we talked about this. So yeah, go ahead, Dean.
Yeah, sorry, the maths is a bit over my head on this one, so I was trying to think about it more conceptually, and what I came to, and correct me if I'm wrong, but like the normalizing flows, effectively you're trying to resolve an entire vector field, and in the conditional flow matching, you're effectively ray trace. It's like ray tracing. There's a ray tracing technology there. And then with the marginals, it's almost like piecewise ray tracing. Like you're taking all those rays you've traced between all the arbitrary sets of points on either side, between the two different distributions, and standing at some point in the middle and saying, right, most of the rays pass through this point here, go towards, the bottom, the bottom on one side and the bottom on the other side. That's kind of like wrapping a ribbon around the dense regions of rays that you've just traced for the conditional, something like that. Does that sound about right? Or
I think it's a little bit different, and it's the reason why so the right picture is kind of magic that this happens. This just happens because of like some math that falls out of something of ordinary differential equations. It's not intentional, and it's not something that was figured out. It's just like they're lucky that it works this way. That's how I would put it. Because even though you're training it with all these intersecting paths, the fact that they're using an ODE solver to do the left one, I mean the right plot, means that they can't have intersecting paths. So they're not choosing for them not to be intersecting, they just can't be intersecting.
But isn't the idea that if I take a point in the middle, on the left picture, right, where there is a crossing, I marginalize over the points on the left, which is my z coordinate, as they call it. I should get for each point, and I do this essentially the flow on the right. I thought that was sort of the
yeah, you're right. If you marginalize over it, yeah, you should get the flow on the right.
Yeah, I find
I guess in that way, yeah, what Dean said is correct. You're right. Good point.
Yeah, I just find it strange that actually works, but I guess the math works out that way.
Yeah. It's pretty, this is all really complicated stuff, which isn't great for like making it accessible to people who are getting into machine learning. But I do think it's really cool, and it does work quite well. And maybe over time we'll start getting like better tutorials on this, because I have to say that while the tutorial was really well written, I felt there was still a lot of places where like there were some notation errors, and like I think things could have been explained a little bit better. But anyway,
What's left but is right. I thought that they go from Gaussian to Gaussian. It made it to some extent more confusing because you never quite knew which direction actually they're currently talking about.
yeah, good point. But okay, so cognizant of time. So conditional flow matching is great. Like this whole way of training these networks is great, but it has two issues. Like it often leads to non-straight marginal paths, which means sampling is slower. And then like it also means that when you're training, you have like many different paths that will lead to the same point, because each time you sample a new path from like here to here, and that creates like high loss variance, which means that like you could take one picture in one epoch and have a loss of 100, and then the next one have a loss of 2, and then the next one have a loss of 200. So like this lack of consistency, even though you're learning, means that it takes a lot longer to learn. So this is where like, oh man, I wanted to show you. I'm gonna just bring it up over here. I thought I put the right plot in, but I didn't. Back. There you go. Okay, so just to give an idea of what that means or what that looks like is over here. So you have another, you want to go from, let's say like you want to go from left to right. And this is what it would look like during training, where if you are constantly sampling like what point from here to here, and you get a lot of these crossing paths. And then when you marginalize, you're going to get like some paths that go down and up instead of going straight across. And that creates an issue where like you have these like really long paths, which will slow down sampling. And that's one of the issues with this approach that's being taken, what I would call like the naive approach. And that's where conditional flow matching with mini batch optimal transport comes in. And it's actually like super simple. So this is like the approach that they take now, or the approach that they were describing. And this is with optimal transport. And basically what they do is I have the steps written down here. So you randomly select endpoints from your original data set. You get like, so you get 10 images, and then you randomly select and you sample endpoints from a simple distribution from like your Gaussian or wherever. And then you use something called like the Sinkhorn algorithm to pair those points such that I think you minimize the average distance between any of the 2 points. And what that means is like there should be as straight a line as possible. Yeah, go ahead, Arvid, as possible between any 2 points. Yeah, Arvid?
Yeah, one thing that I found slightly surprising was that we train these to find representations, right? So you put representation learning as one of the objectives.
Mm-hmm.
Now, if we do this, don't we already put quite a lot of structure onto the initial distribution of where stuff goes to where? Because say if the mini batches are big enough, then this random sampling will pretty much always ensure that similar points would come from similar regions in your input space. And so wouldn't that be against having a learned representation per se?
Not sure, to be honest, because I think the whole idea is that you're always going to, with either approach, in theory, you should learn the data generating distribution.
Yeah.
But as you point out, like with the second approach, you have like similar points from your simple distribution will lead to the same points in your other one. I don't know if that's good or bad, to be honest, like whether that's useful or not useful.
Because if you think if you move, say between 2 points in the input space. In the past, points between input space points should be also valid representations. But I think if we do this optimal transport, if you look at the picture, right, you get essentially flows that are non-overlapping. So at some point we might be making a jump there also.
Yeah, true.
Yeah, I don't know. It's hard to wrap your head around, especially since this goes into very, very high dimensions normally, right?
Yeah, exactly. And it's hard to tell like what this would even look like, what these plots would look like if you were to do it at that point.
Yeah.
Oh,
thank you.
Okay. So yeah, optimal transport. I won't go into optimal transport. I feel like I went a bit too deep on the math in this one. But the basic idea of optimal transport is like, let's try to create as straight a line as possible between like our input dimension and our output dimension for all the samples. And I think this is like a really funny, if you read the tutorial, it goes through like so much math. And then at the end of the day, what they're doing is like drawing a straight line from their input space to their output space, and then training a model to like correctly trace that line. So most of the math that is being used isn't that we saw isn't being used here. You just and yeah, so it's like the final training that they're doing is so much simpler than all the math that we saw. Anyway, yeah, go ahead, Dean.
Yeah, I wonder, is that kind of the point though? I mean, that this approach is far simpler and more efficient.
Yeah, probably.
How complicated the alternatives are.
But I guess for me, it would, the reason why I say that, but definitely, and I think that there's an elegance and simplicity for sure, is that if they just wanted to tell us to describe to us how people do things today, you could do it without, or using these methods today. I feel like you could do that without any math, where you say like, we have this distribution, we have this distribution, and we sample points from one and we match them with the other, and then we trace a line between them and we train it that way. So like the explanation of it doesn't require you to know about like Lipschitz continuity or differentiability or like any of this stuff.
Right, yeah, I get your point, yeah. That's fair.
But definitely I think that's the whole point. It has to be simple in order for it to be computationally efficient. So like a quick summary, I'm cognizant of time, is that, so of the whole tutorial is like, one way to learn a data generating distribution is using a model based on normalizing flows. One expressive form of normalizing flow models is residual normalizing flows. Continuous normalizing flows is a form of residual normalizing flows that requires less hyperparameter tuning and satisfying less difficult mathematical assumptions. However, it requires expensive ODE simulations at training time. So we use flow matching because it provides a way to train continuous normalizing flows without ODE simulations, but can be slow to train and slow to sample from using a naive approach. So we use flow matching with mini batch optimal transport because it trains faster and leads to quicker sampling. That's the tutorial in six sentences. Cool. So yeah, thanks everyone for listening. I feel like it was whistle stop and a little bit not my best presentation, but I hope you took something from it.
Thank you very much. I thought it was great. And yeah, good luck on your future endeavors.
Thanks.
Where are you going again? Do you know?
Yeah, I'm going to a company called Lawhive. It's another startup in London.
Great.
Yeah. We have there's a paper club next week. I won't be at it, but I'll still be attending paper club, so I'll see you all here.
Excellent.
And have a good weekend.
You too. Thank you very much.
Thank you very much.